Okay, good morning to all. Welcome back for today's class, process synchronization and semaphore. So, first, a cooperation process is one that can affect or be affected by other process executing in the system. Cooperating process may either directly share a logical address space or be alerted to the shared data only through files. This concurrent access is known as the process synchronization. Generally, there are two kinds of synchronization are there. One is your control synchronization, and then another one is your data access synchronization. In control synchronization, process may wish to coordinate their activities with respect to one another, such that a process performs an action only when some other process reaches specific points in their execution. Data access synchronization, the race condition should not arise when concurrent process share data. Data access synchronization is used to ensure this by implementing mutual exclusion over access to share the data. So before that synchronization, let's come to the what is the critical section problem. Consider a system consists of n number of processes P0, P1 and Pn minus 1. Each process has a segment of code which is known as critical section, in which the process may be changing common variable. That means what is the critical section of a problem? The area or the section where the process may be changing the variable, updating a table, writing a file and so on. The important feature of the system is that when the process is executing its critical section, right, no other process is to be allowed to execute in its critical section. That means if one process is trying to change its variable or updating any table or writing a file, in that same time no other process is allowed to execute in its critical section. So the execution of critical section by the process is a mutual exclusive, right? It's a mutual exclusive. The critical section problem is to design a protocol that the process can use to cooperate. Each process must request permission to enter its critical section. The section of code implementing this request is the entry section. The critical section is followed on exit section. The remaining code is the reminder section. So, example Y1, entry section, critical section, exit section, reminder section. That means when you're writing a program, suppose using the while condition, that is the initialization of the variable entry section. Critical section means so what? Now critical section where the actual variable, the value of the variable is changed, updating the table, writing a file, whatever. So that is the critical section and the exit section, and out of this others are known as the reminder section. So main thing is that when one process run in its critical section, no other process allowed in its own critical section. So that is the main thing. That means this critical section problem is a mutual exclusion thing, right now. So solution to the critical section problem must satisfy the following three conditions. One is your mutual exclusion Then another one is your progress, and third one is your bound waiting. So these are the solution to the mutual exclusion processes. So first come to the mutual exclusion. If process Pi is executing in its critical section, then no any other process can be executing in their critical section. Whatever I have discussed, if one process is executing in its critical section, then no other process is allowed to enter its critical section. Next is that progress. What do you mean the progress? If no process is executing in its critical section, and some process wish to enter their critical section, then only those processes that not executing in the remainder section can enter its critical section. Next, that means progress means what? If no process is executing in its critical section and some process wish to enter their critical section, then only those processes that are not executing in their remainder section can enter its critical section. Next is your bounded waiting. There exists a bound on the number of times, then there exists a bound on the number of times that other processes are allowed to enter their critical section after the process has made a request. So this is the solution of that critical section. First thing is your mutual exclusion, where if process Pi is executing its critical section, then no any other process can be executing in their critical section. Progress means if no process is executing in its critical section and some process, suppose P1 is a process wish to enter their critical section, then which condition they enter into their critical section? If P1 is not executing in the remainder section, then it can enter into the critical section. Next is your bounded waiting. There exists a bound on the number of times that other processes are allowed to enter their critical section after process has made a request. There exists a bound, again I am repeating, there exists a bound on the number of times that other processes are allowed to enter the critical section after process has made a request to enter its critical section and before that request is granted. That means bounded waiting means what? Suppose there are 5 number of processes, P1, P2, P3, P4, P5. Each time P1 and P2 running in its critical section, but then no chance given to the P3, P4 and P5. So what will happen? Now only P1, P2 only run into their critical section, but P3, P4, P5 never will get a chance to enter its own critical section. So that is the bounded waiting, means there is some limitation. Right now there is a limitation for executing within that critical section, executing within the critical section of the process. Clear? So this is all about the critical sections thing. Next come to the semaphore. What do you mean the semaphore? For the solution to the critical section problem, one synchronization tool is used which is known as semaphore. A semaphore S is an integer variable which is assessed through two standard operations such as wait and the signal. Okay. So thank you for today's class. Next class we are going to discuss about CMOS. So thank you.